The project title is Context Aware Visual Question Answering, in short CA-VQA. So let's dive into the problem background. So firstly, computer vision. Computer vision is a subset of AI and deep learning mechanisms. It is the process of developing techniques to give sight to computers. So the selected domain, visual question and answering, is a computer vision problem that is being actively researched on. So visual question answering, shortly known as VQA, is the process of identifying, processing, and understanding visual and linguistic data to answer questions about any given question. Provided an image and a natural language question, the VQA task tries to provide the correct answer as an output by using the processed visual elements of the given image and the deduced data from the natural language question. VQA has been a crucial turning point for humans interacting with computers. There are multiple applications of VQA tasks, which include helping people with disabilities, such as aiding the visually impaired, and also other potential applications such as virtual assistants and autonomous agents. Designing a VQA task that could generate answers accurately to questions asked from a given context can be a very cumbersome task. This is because the current VQA tasks and the datasets are restricted to only images. So by nature, breaking down images to analyze and understand its contents are harder due to the high complexity of the image. So an image is more rich in content, therefore make it more complex compared to text. So analyzing the image is much more harder than compared to analyzing the analyzing and understanding the textual semantics. Therefore, the current VQA tasks are missing out on a deeper understanding of the context. So moving on to the gap that I identified, is that there are limitations when it comes to arriving at better answers. This is mainly due to the complexity of the image. Therefore, the author of this research has concluded that taking a third input could possibly contribute to arriving at better answers. So this concept map will be used to talk about the technologies, the existing work, evaluation techniques, the data sets and tools that were considered for this research project. So looking at the technology, technology we have artificial intelligence, and under artificial intelligence there is deep learning, computer vision. So deep learning has supervised learning, under which there is word embeddings, recurrent neural networks, and convolutional neural networks. So for convolutional neural networks, which is used to extract the image features, there are three variants of convolutional neural networks. One is the ResNet, the other AlexNet, and ResNext. So ResNext was chosen as the convolutional neural network variant. And then for recurrent neural network and for word embedding, Glove and Groove were chosen. And as for the computer vision, there are two approaches, which is the attention-based approach and the bilinear pooling, for which attention-based approach was selected. When it comes to evaluating the model, um, a qualitative approach, which is interviews, were selected, and a Confucius matrix and accuracy testing, as well as non-functional and functional testing were done. As for the datasets, there are two main datasets, one being the VQA 2.0 dataset and the other being MS COCO dataset. Both datasets were used, and as for the tools, Python was used as a language, Anaconda and Google Colabs was used as the IDEs. React was used as the front-end framework, and PyTorch, NumPy, and Matplotlib were used for the model. So the proposed solution is illustrated in this high-level architecture diagram. So the high-level architecture diagram is a tiered architecture diagram which has 4 tiers in this case. So the very first tier is the presentation tier, which consists of a web application. The second tier is the delivery tier, which is the REST API. And the third tier is the logic tier, which has the backend of the system. And the fourth tier is the data tier, which has the data set and the previously trained models. So going back to the delivery tier, the REST API connects the web application to the backend. So the backend has the feature extraction module, which consists of the image feature extractor, the question feature extractor, and the additional feature extractor being the caption. So the caption feature extractor was added by the author as the images are, as stated earlier, the images are more complex for computers to analyze what's in it. Therefore, adding a third input, which is a caption, which is a text, which describes the image, would be much easier for the computer to understand what is actually going on in the image. So once the features are extracted, it is passed into a feature fusion module, where the features are fused together, and then that is passed on to a prediction model, which would predict the answer. So that's the proposed solution. Next, let's have a look at the prototype. This is the web application that was developed to demo the prototype. So the user has to select an image, enter the question, a description, submit it, and the system will return an answer. So let's select an image. Let's type in a question. And submit it. It gives a status, and the system returned the answer as giraffe. So let's ask another question on the same image. So that's 2 animals, and we could ask another question. returns brown and white as the answer. So this is the prototype, a very simple prototype. So moving on to the implementation of the prototype. So initially we import important libraries and packages, and then the dataset has been unzipped and loaded into the environment. So this is the dataset class, which handles the pre-processing of the dataset. So this filters the dataset by the top 1000 answer classes, or any the number of answer classes that are required. This filters the dataset to take the first n number of data, and this handles the tokenizing of the questions, answers, and the captions for the training and validation sets. So it removes periods and other punctuations. It converts it into lower text and splits them into individual words. After that, the questions and the answers and the captions are encoded. Also, vocabulary creation is done, which identifies the most awkward words and orders them in decreasing order. So the most awkward word is assigned 0, and the next awkward word would be assigned 1, and so on and so forth. So here the questions and the captions are padded based on the maximum length of the question or the string. So in this case it was 30, since the maximum length of the string was 26. So this padding is done so that the input sequence to the RNN module are of the same length. So here we are inserting the encoded questions and the captions and the answers into the training and the validation data set, validation dictionary. So this is specifying the data set, whether it's the trained data set or the validation or the test data set. And these are the functions that were used to perform padding. This is to get an item from the dataset class. The image is normalized and converted to a tensor. The dataset is created for use in the model, and it is loaded into the data loader. So I have loaded taken the top 1000 answer classes for this dataset. This is the trainer class. We are creating an instance of it and calling its methods would train the model. So this is the get device model, which would get the device, the current device it is in. This is the evaluate function, which evaluates the model. This is the predict model, which takes in an individual question, caption, and an image, which returns the predicted answer. So the model is trained for a specified number of epochs and calculates the loss and adjusts the weights of the model based on the loss, with a goal to decrease the loss. This calculates and returns the accuracy of the model. This is the custom data loader class, which moves the data to the device, either the CPU or the GPU. This is the value for the unknown embeddings in the glove vector. This is the main model class, which is the CA-VQA model. So this function calculates the train loss for each batch in an epoch. This function calculates the validation loss and the accuracy for each batch in an epoch. Here the model gets initialized. So this part is responsible to extract the image features. So the ResNext 101 model has been used as a pre-trained model, which was pre-trained on the ImageNet dataset. These are the question and caption feature extractions, basically the textual feature extractions. Generating glove weights, and the generated glove weights is inserted into the embedding layer. And initializing the RNN model grew with the hidden sizes and number of layers, 2 different grooves to extract the features of the caption and the question separately. The dropout has been added to regularize the model. So initializing of linear layers for the extracted features from the question and the caption is over here. So this is the forward function. The image features, the caption features, and the question features are extracted over here. So the image features and the caption, the question features are combined. Then the image features and the caption features are extracted. That were extracted are combined. The question and the caption features that were extracted are combined. Then the combined image with question and caption features are combined, and this combines the previously combined outputs. All of this goes through an output layer to predict the final answer. So actually the reasons for all of these combinations is to understand the features better, and this is actually where the model is created, and an instance of the trainer class is created. This is the model is being passed to the trainer, and the trainer starts when the training starts when training.fit is called. Once the training is done, this is used to plot the accuracy for each epoch. on a graph, and this plots the loss for each epoch on a graph. This plots the learning rate for each patch number on a graph, and this is used to test and test the prediction of the model, and this finally is used to generate the confusion matrix, the accuracy score, the recall score, the precision score, and the F1 score. So that's the implementation of the model. This is the implementation of the backend. Flask has been used to expose the API. So there is this get data function, which has the image, question, and the caption that was sent from the web application by the user. And so the questions and the captions are encoded with the padding with a sequence of 30, and padded with a sequence of 30, and all of these are passed into the model, which then returns the answer as a prediction, and this answer is returned back to the web application to be rendered for the user to see the answer. So that was the end of the prototype demo. Next, let's have a look at the evaluation. So evaluation was done using the confusion matrix. So these were the results of the confusion matrix. So the accuracy of the model is 59.19%. The precision of the model is 62.34%. Recall is 59.72%, and the F1 score is 59.89. Benchmarking was also done for evaluation. So some of the previous existing research were used to benchmark the accuracies of my model. So the last row here are the accuracies of my model on the VQA 2.0 dataset for different answer types. So for yes or no answer types, the CA-VQA model has an accuracy of 76.09. For number answer types, it has an accuracy of 31.62, and for other answer types, it has an accuracy of 54.38%, and it has an overall accuracy of 59.19%. The future works is that the model used pre-trained models to extract the image and textual features such as ResNext and Glove. So using custom models trained on this specific dataset could lead to the model performing better in terms of accuracy. There is also a clear room for improvement for the how many type questions, which are questions that require a number as the answer, and this can be clearly seen in the benchmarking. The model has an accuracy of 31.62%, which is far less than the existing work. And the final future work is that the model can be easily extended to other languages given the availability of the dataset, because right now it's done only for English. Yeah, so that's about uh, the whole presentation.